Hello and welcome to the channel. This is another video about numerous nested square roots, and this task looks simpler to me than the previous one, the link to which will appear on the top of the video. This time you have two problems related to each other. Just start with smaller amounts of square roots and try to find the pattern. Once the formula is found, use common sense to solve the problem. So pause the video and do it. Now you are welcome to see how I did it. So let a sub I be the expression with I nested square roots. The sequence can be defined recursively. A sub 0 is 1. A sub I equals square root of n times a sub I minus 1 for positive values of I. Our objective is to find what is called closed formula, an expression that allows to find the value of a sub I straight from its index I without going through the recursion. Let's start with smaller indices to find the pattern. A sub 1 is just square root of n, or n to the power of half. For a sub 2, we use the recursion formula and substitute the expression for a sub 1. Now we can merge the factors under square root and replace the square root with raising to the power of half. I deliberately didn't add up the exponents in order to make the pattern more obvious. Next we need to halve each term of the sum, and it looks like the pattern is revealed, doesn't it? However, for certainty, let's get the expression for a sub 3. And we substitute the value of a sub 2, and again merge the factors under the square root, and again halve each term in the exponent for n. Probably this is what you expected to get, and I expected that as well. So let's make a guess. A sub I is n to the power of the sum of a half, half squared, etc. up to half to the power of I. This is not quite a closed formula, as it contains ellipses. Can I think of a way to improve it? Fortunately, we can get rid of the ellipses by noticing that elements of the sum form a geometric progression. Where the starting element is a half, the ratio is also a half, and the number of elements is I. So we can evaluate the sum using the well-known formula for the sum of elements of geometric progression. Given the starting element, the ratio, and the number of elements, the denominator is evaluated to a half, which cancels out with half for the starting element, so the result is just the numerator, which can be expressed as 1 minus 2 to the power of negative I. The obtained expression has to be used as the power of n in the closed formula for a sub I. So this is our guess about the closed formula, expected to work for all non-negative values of I, which yet needs to be proven. And we prove it, of course, by induction. The base is straightforward. For I equals 0, the suggested closed formula gives n to the power of 0, which is 1, exactly matching the definition. The transition isn't difficult either. Assuming the formula to hold for index k, we apply the recursion formula to a with index k plus 1. Substitute the assumed value for a sub k. Again we merge factors under square root. This time I added the exponents given that the pattern is already known. However, that didn't help much, as we still have two terms for the power of n, and each of them needs to be halved. Half of 2 is of course 1, And we also need to multiply 2 to the power of negative k by a half. Given that half is 2 to the power of negative 1, this means adding negative 1 to negative k. Therefore, the result is n to the power of 1 minus 2 to the power minus k minus 1. And in order to make it really obvious, we can place minus before the brackets. The obtained expression matches the suggested closed formula for index k plus 1. The transition is complete and the closed formula is proven. However, neither of the problems have been solved yet. Let's start with problem 1. Now we know the closed formula for a sub I. We assume n to be an integer greater than 1, and we need to find the lowest value of n so that a with index 2022 is an integer. Let's for brevity replace number 2022 with the letter t. I decided to use capital T for better visibility. Let's write the formula for a sub t. Here, instead of 2 to the power of negative t, I used a less fancy expression, 1 divided by 2 to the power of t. Then we reduce the exponent to common denominator, making it equal to 2 to the power of t minus 1 divided by 2 to the power of t. And the value of a sub t has to be an integer. Try to continue from here. We are going to prove that the numerator can be replaced with 1. In other words, in order a sub t to be an integer, n to the power of 1 over 2 to the power of t must be an integer. As start, let's prove statement 1. Two consecutive positive integers are always co-prime. In other words, the greatest common divisor of c and c plus 1, where c is a positive integer, is always equal to 1. So let d be the greatest common divisor of c and c plus 1. This means that d is a positive integer and d is a divisor of both c and c plus 1. In other words, c equals d times p, where p is an integer, and c plus 1 equals d times q, where q is also an integer. Subtracting the first equality from the second equality gives 1 equals d times q minus p, which means that d is a positive divisor of 1. However, number 1 has only one positive divisor, which is 1 itself. Therefore, d must be 1. But d is the greatest common divisor of c and c plus 1. Therefore, the greatest common divisor of c and c plus 1 is 1. The numbers are co-prime and statement 1 is proven. Since there is statement number 1, you certainly assume that there must be also statement number 2. Here is statement number 2. If n is a positive integer greater than 1, u and v are co-prime positive integers, and n to the power of u over v is an integer, then n to the power of 1 over v is also an integer. Any integer greater than 1 has a prime factorization. So n equals p1 exponent alpha 1, p2 exponent alpha 2, up to pm exponent alpha m, where p's are distinct prime numbers and all alphas are positive integers. Then we get the expression for n to the power of u sub v, and this value is given to be an integer. Let's take for granted that in this case all factors must be integers. This may appear not quite obvious to some ones, however the strict proof of that would probably need a separate video, so I'll better skip it. Since each factor is an integer, its exponent must be a non-negative integer. The proof of that looks simpler, so you can try it on your own, but I will skip it as well. In this case, the value of exponent is a positive integer, as all the terms forming it are positive. So alpha sub I times u is divisible by v. But u and v are coprime. Therefore, alpha sub I must be divisible by v. This property of coprime numbers is mentioned in numerous sources. Some of them even prove it. So with your kind permission, I will skip the proof again. Let beta sub I be alpha sub I over v. Then beta sub I is a positive integer for any index I. Therefore, alpha sub I equals v times beta sub I. And after we substitute the expressions for alphas into the equality for n to the power of u over v, all these are cancelled out and the right hand side becomes more compact. It can be made furthermore compact by erasing both sides into the power of 1 over u. Since all betas are positive integers, the right hand side is an integer. Therefore, n to the power of 1 over v is an integer, and statement 2 is finally proven as well. The rest is straightforward. 2 to the power of t minus 1 and 2 to the power of t are two consecutive positive integers. Therefore, according to statement 1, they are coprime. Then, from statement 2, it follows that n to the power of 1 over 2 to the power of t is an integer. So, the question mark may be removed, along with the statements which have completed their proud mission. And you have a chance to complete the solution on your own. So let k be n to the power of 1 over 2 to the power of t. We already know that k must be an integer. Moreover, since n is more than 1 and the exponent is a positive number, the value of k is more than 1, that is, no less than 2. Using the definition of k, we can express n in terms of k. For someone who may be unaware, if a power tower contains 3 or more levels, the topmost exponentiation is implemented first. In this case, we first raise 2 to the power of t. The result is used as the power of k. Now we can also express the value of a sub t in terms of k. A sub t equals k to the power of 2 sub t minus 1. We see that a sub t is indeed an integer, and it is exactly k times less than n. Since the power function with a positive exponent is increasing, the lowest value of n is obtained when k equals 2. So the answer is 2 to the power of 2 to the power of 2022. And the corresponding value of a is 2 to the power of. Here I make a short pause and continue. 2 to the power of 2022 minus 1. It only remains to solve problem 2. This time there is an infinite number of square roots, which looks logical to denote as a sub infinity. It is claimed that a sub infinity exists, and moreover, it is an integer for any positive integer n. Let's find out if this is really the case. Or you may prefer to do it on your own. An operation repeated infinite number of times means the limit of this operation repeated finite number of times, when the number of times tends to infinity. So a sub infinity is the limit of the expression with k square roots when k tends to infinity. But the expression with k square roots is a sub k. And for a sub k, we have a closed formula, which looks very handy here. We only need to observe that since exponential function is continuous, we can safely move the limit to the exponent. And when k tends to infinity, 2 to the power of negative k tends to 0. Therefore, a sub infinity is n to the power of 1, that is just n, and n is an integer. The only thing remained is to wish that everything were as easy as that. And this is, of course, the end.